Okay, we're at Berkeley time, so let's get started. So just a quick reminder, if you have not already figured out who your groups are and who your partners are for the project, that is due soon, or it's, right? So it's due with the homework, right? Good, I'm glad you remember. So make sure you figure out exactly who you want to work with, how you want to work on it. Remember that basically if you choose to do a project with other people, we will hold you to it. It is not okay to get a group of people together and then bail at the last minute, okay? So keep that in mind. The form will also ask you for which project you want to do. The choice of the project is not binding. Like you could say, oh, I want to do the neural networks project, and then later decide that you want to do the gradient descent project, and that's totally fine. But what is binding is the fact that you have chosen to do it with a group, and then they're required to continue with that group. Okay? Good. So that's the one thing I wanted to remind everyone about before we start. So now we've gone through, basically last week you saw a lecture on second-order cone programs. So you've seen now LPs, which are a very special case, QPs, which are basically a generalization of LPs in some sense, right? Like all LPs are QPs. And then you saw second-order cone programs, and you saw that QPs and LPs are basically subsets of the set of SOCPs, right? So there are three specific types of optimization problems. And the nice thing about these optimization problems is that you can actually have specialized algorithms that can solve each of these efficiently. So we talked a little bit about simplex in the context of LPs, in the context of quadratic programs and SOCPs. In the most general cases, what you will use for this kind of problem is what is called an interior point method, which we may or may not have time to talk about in this class. But the basic idea is that you use the primal and the dual jointly in an algorithmic form and use the certificate property of the dual to basically find a point that is within epsilon of the optimal point. Okay? So that's kind of the strategy that will be used for solving these problems, and these can be solved efficiently. And that's why LPs, QPs, and SOCPs are particularly important and particularly interesting to us. Today we're going to move to another set of problems that have a different kind of property. And so what we've been talking about so far, we've often talked about whenever we're doing regularization, whenever we say, let's consider a cost function. We started out this class with thinking about the least squares problem, right? And the least squares problem was basically a quadratic problem. Then we also talked about the minimum norm problem, right? And all of these things, we're saying, hey, we have a particular set of constraints, and we want to minimize the L2 norm of the error, or the L2 norm of the solution, right? We've been focused very much on the 2 norm, because the 2 norm is nice. The 2 norm is nice. It's differentiable. You know, you get these nice quadratic things that in often many cases, unconstrained quadratic problems we can solve explicitly, which you now know generally. But turns out that considering the L1 norm also has lots of special properties, and that's kind of what we're going to explore in today's lecture, okay? So I want to start out with the parallel, L1 parallel to a min okay? So let's consider now this problem. I've written this a little ambiguously intentionally, but when I look at this problem here, okay, I'm saying, well, look, I want to look at all of the solutions to ax equal to b. In general, if a is wide, this will have infinitely many solutions. And of those, I want to choose one. And typically, we've chosen the one with the smallest 2 norm, right? We said let's choose the one that minimizes the energy. But what if instead we said, what is the minimizing L1 norm solution? Okay? What can we do in this kind of scenario? What might this lead us to? Okay? So here, let's first think about, can we even solve this problem, right? So let's assume first that A is full row rank. Okay? So looking at this problem, what kind of problem is it? Is it the kind of problem we like? Is our objective convex?
No.
Objective not convex? It's a convex problem, right? What's non-convex about it? Norms are convex in general. This is a convex objective, right? And the constraints are affine. So this is a convex problem, right? So we like this. But what is the one thing about this that maybe we don't like so much? It's not differentiable, right? The L1 norm is not differentiable. The L1 norm is basically the sum of absolute values. And remember, absolute value has that one point at 0 where your function is not differentiable. It's differentiable everywhere else except for that one point. It's a continuous function, but it's just not differentiable everywhere. Okay? But now, can we do something to turn this into a kind of problem that we know and like how to solve?
Adding slack variable.
Right. We can use slack variables, right? This is exactly, we've used this trick before. And so when we had an L1 norm before, what did we do? We replaced that L1 norm with what? We replaced it with a slack variable, and then we added a constraint, right? And so we did that one particular way. We did that for the lasso problem, which we're going to talk about in the second half of this lecture. Here I want to show you a different trick on how to convert this, again, to something that's nice. In fact, we're going to convert it to a linear program, okay? So just as a reminder, if I consider the L1 norm, let's say 1 to n, xi, right? It's the sum of the entries of xi. Okay? So I'm going to do something similar to what we've seen before, but it's kind of similar to the trick that we did for linear programs. Remember the trick that we used for linear programs if we wanted to convert all of our variables to being non-negative? We said that every real number can be expressed as the difference of two positive real numbers. Remember we did that trick? So we're going to do a trick similar to that. We're going to say xi, I'm going to write xi equal to xi plus minus xi minus. Okay? And I want to say that xi plus greater than or equal to 0, xi minus greater than or equal to 0. These are also slack variables. And now I want to say something further, okay? I want to say that I want to find xi plus and xi minus such that the absolute value of xi is equal to xi plus xi minus. Okay? I want to claim this. I want to claim that I can find such xi plus and xi minus. It's not obvious that one can find such things, right? But could you think about how you might be able to find such things? What's an example? So for example, try this out, right? Let's say xi was equal to 3. How could you figure out what xi plus and xi minus were? Can you think about something?
1, 2.
So what's one easy thing to choose for xi plus?
Divided by 2.
Divided by 2. Okay, that's...
3.
And the easiest solution is 3, right? And what would you choose as xi minus? 0. And do both those things satisfy? What if xi was equal to minus 3? You choose xi plus as 0 and xi minus as 3 again, right? So turns out that we can actually pretty easily satisfy this condition. If I have xi plus always equal to xi, if xi is greater than 0 and equal to 0 otherwise, xi minus is equal to minus xi if xi is less than 0 and is equal to 0 otherwise. Then I have now satisfied both of these constraints, right? So I have basically gotten rid of my absolute value by rewriting as these two variables, both of which now I have constraints on as being greater than or equal to 0. Right? And so I can rewrite my optimization program as minimize sum xi plus xi minus, and then I have a times xi plus, or x plus, I guess, sorry, where x plus I'm just thinking of as the vector of all xi pluses, right? Is that clear to everyone, what x plus is? Minus a times xi minus is equal to b. All I'm doing is in this constraint up here, right? I'm substituting x is equal to x plus minus x minus, right? This I can choose to then write as x is equal to vector x plus. And I'm just substituting this into that constraint up there. And then I also have now xi plus greater than or equal to 0 and xi minus greater than or equal to 0, right? And I can write this as my new optimization problem. And now this looks like something that's a standard LP, right? We've seen how to do this before. Nothing particularly special about it, right? So even though we had this non-differentiability, we've put it into a format that we know how to solve. Why do we say norms are convex in general? I guess maybe we haven't technically proved this, but norms are convex in general. You can use basically the first order property. Sorry, you can use the basic Jensen inequality to prove this. But if it's not obvious, definitely come talk to me. Because these are two different things. This is xi, and this is absolute value of xi. We're saying, can we find xi plus and xi minus that satisfy both of these things? And turns out we can, because if you choose xi plus always equal to xi when xi is positive, and xi plus always equal to minus xi when xi is negative, then you notice that xi plus minus xi minus is always equal to xi, right? Check for this, that this equation is satisfied and this equation is satisfied. Great question. When is it preferable to do this trick as opposed to just using the normal slack variable or the epigraph reformulation? There's not necessarily like a, a flowchart rule book for this. This is like one of those things that there are different ways to do a thing, and depending on your situation, you might prefer one over the other. The advantage of this is now you get this non-negativity constraint on your variables. And you might value that in certain cases. You might not value it in other cases, right? If you have an LP solver close at hand, maybe you want to have this non-negativity constraint in there. That will make your life easier. Okay? So the thing that I want to now bring about here, which is the same thing as in the epigraph reformulation, right? In the epigraph reformulation, we added slack, right? We added some freedom to our system. Similarly here, when we look at this particular setup, we're not adding this or this as constraints to our system. Does everyone see that? We're not writing those. So how do we know, how do we guarantee that those constraints are actually satisfied? How do we know that basically we're always going to end up with xi plus or xi minus being equal to 0, or xi itself? How do we know that this is actually going to be satisfied, right? Because this is true only if you choose xi, like xi plus and xi minus according to these rules. Does everyone see that? It's not true always. It's only true when these rules are satisfied. So how do we know that at optimum, these rules are actually going to be satisfied? Does everyone understand the challenge we have introduced for ourselves? Okay? So how do we now argue this, or how do we deal with this situation? So intuitively, what's happening in this problem, right? When I look at this optimization problem, what is the objective function doing? What is the optimization trying to do? It's trying to minimize this quantity, right? And remember now, both of these things are positive or non-negative. So it's trying to make them as small as possible, okay? Can we use that fact that there's this kind of downward pressure to argue basically that the constraint that we have in mind must always be satisfied? So basically what I want you to think about is, look, if I have two non-negative things and I'm pushing both of them down, they have some relationship between them. But if neither of them is 0, can I kind of get somehow a better solution by pushing at least one of them down to 0? Is that kind of the way of thinking about something like this? Or how would you try and go about proving something like this? Is that intuition clear? Like if I have xi plus somewhere and xi minus somewhere, right? What is important to me in terms of xi plus and xi minus, in terms of satisfying the constraints? The gap between them is what matters, right? Look at my constraint here. My constraint is A times my constraint depends on the gap. Just give me 1 second, okay? And so if my constraint depends only on the gap, is there a way to make sure that all my variables are satisfying my constraints, but kind of make things better if both of my variables were strictly greater than 0? Like, okay, so I'm going to give you a minute, and I want you to think about how you could turn this kind of intuition into a rigorous proof. In the meanwhile, I'll take this question. So the question is, by construction, isn't one of them going to be 0 already? That's what we want, but when I look at the optimization problem that I'm solving is only what is in this box. Have I written these constraints explicitly in this box? I have not, right? So when I put this into a computer and ask the computer to solve it, nowhere are these constraints being checked. So I need to somehow guarantee through my math that even if I input this program in, I'm going to get a solution to the program that I originally cared about. Okay? And that's exactly what we're trying to argue. Okay, so how do we approach this problem, right? So you want to give a solution? Or?
Yeah.
Okay. Yeah, I want to just talk through it together for a bit, okay? So now let's think about this. We have this xi plus, and we have xi minus, okay? So to say that to rigorously argue, okay, that we want to have at least one of them 0, I'm going to say, well, first let me say without loss of generality, let's have, for example, that xi plus greater than or equal to xi minus strictly greater than 0, okay? One of them has to be bigger. Let's call xi plus the bigger one. It doesn't really matter which one. But now let's assume that both of them are strictly bigger than 0, right? If one of them was 0, then automatically the other must be exactly equal to xi, right? Or minus xi, depending on the situation. Do you see that? Basically because of the way things are set up. So basically we need to just say that one of them needs to be 0. So why is one of them going to be 0? So let's say, for example, that both of them are distinct from 0. Okay? So now if I define, for example, some variable, let's call it xi plus new, the new version of xi, what do you want to define as the new version of xi? How could you guarantee that your constraint is still satisfied given these two? You know that xi plus and xi minus satisfy your constraint. How could you do something? How could you create another variable, set of variables, that also satisfied your constraint? Remember, you have xi plus minus xi minus here. So what would you substitute here and here to maintain the gap between these two things? You could put minus here, but then you'd multiply both sides by -1. That wouldn't work. So I have a. So what is this quantity here? This is x, but in our notation here, right? I have a times the difference between these things is equal to b, right? So a times xi new or is also equal to b, right? Does everyone see that? Because xi plus new is basically just the difference of these two things, right? If I define this as xi plus minus xi minus, right? If I define this new x to be just the gap between these two things, I can still satisfy exactly this constraint here, right? What would I define now xi minus new in this case? This would just be 0, right? So instead of having x plus minus x minus, I just put x plus minus x minus into the one vector and set the other vector to be entirely zeros, right? That's exactly the same. Like, it doesn't change my constraint at all. Does everyone see that? These new xi plus and xi minus, or x plus new and x minus new, still satisfy the constraint. But now in our objective function, if I consider the original objective function had a term that was xi plus xi minus, right? Our new objective function now has xi new plus and xi new minus. Which of these two terms is bigger? This is something here. What is xi plus new? This is xi plus minus xi minus plus 0. So is this bigger, or is this bigger when we have all of these things being strictly greater than 0? This thing is bigger, right? So when I'm trying to minimize, and I'm searching over all of my points that satisfy my constraint, do these points satisfy my constraint? Yes? Do these points satisfy my constraint? Yes. Which one would I choose to be the minimizer? I would always choose the new points, right? Because they give me the smaller value of the objective. So basically, if I ever had a situation where one of the xi's was distinct from 0, I could always improve my solution by pushing down to 0. Therefore, my optimum must always be attained when one of the variables itself is 0. Does everyone see that? Questions? What we're saying is what matters is the gap between the variables, because that's what the constraint depends on. But because of that, I can always decrease my objective function till one of the variables is 0. Okay? And so I will always be in a situation that these constraints are always satisfied. You know, at least one of these two variables is going to be identically equal to 0. And therefore, this relaxation of the problem, this inclusion of slack variables, is totally fine. Okay? So here we've done a relaxation of the problem. We're changing the setup a little bit. But we're proving that the relaxed version of the problem has the same solution as the original problem. That's not true for all relaxations. That's just true for this relaxation. Okay? Yes?
So is the new xi plus exactly the same as the original xi? Because the way they
No, it's distinct, right? It's different. This is saying, we were saying hypothetically, let's say we had something that was optimum but distinct from 0. Yeah, so now basically what we have shown is that whenever you solve this optimization problem, one of your xi plus or xi minus will always be equal to 0. Right. Therefore, the other variable is automatically equal to xi or minus xi. Yes? Without loss of generality. Okay, so the nice thing is that this is a trick that can be basically used to convert any kind of L1 norm thing into an LP, right? So 1 norms in general are things that we like because we can use them to convert things into, like, we can always convert them into an LP, and LPs we basically always know how to solve, okay? So the same thing is true now, even if I was to consider the L1 parallel to least squares. Right? If I, for example, had the min okay? Least squares has a 2 norm here, right? Now I want to consider the L1 norm. I can rewrite this problem to be equal to min 1 norm of E over E, comma x, such that AX minus B is equal to E, right? So I've basically rewritten this problem exactly into that min norm formulation, which means that that exact same trick can be used to also convert this into an LP, which means this is also a solvable problem. Okay? And it turns out that in some cases, these kind of 1 norm parallels to least squares also have some special properties. So what I want to talk about is now a special case of this. Any questions about this? This is pretty straightforward, right? Yeah? Okay, good. Okay. So now let's consider the following setup, where let's say I have some points, B1, B2, B, how many do I want to have? Let's see, do I want to have n? Okay, let's just have scalar points and let's have n of them, okay? And I want to find, for example, the average of these points. Right, let's just say these are all scalars. These are real numbers. If I wanted to find the average of these points, I can write the following optimization problem, right? Find an x to minimize this, right? This is just a least squares problem for the scalar case. Everyone see that? And what is the solution to this? What is the minimizer of this? We all know. We've done this a lot now. It's just the sample mean, right? It's just the average, exactly. Everyone remember this? We're good? Okay. So now if I was to do the same thing, but now, so let's just say explicitly, instead, what if we considered find the minimum x and think about the L1 norm instead of the L2 norm. Okay? So think about the absolute value. How could we solve this problem? How could we go about doing this, right? So we know that now we can cast this as a linear program, right? So one solution, one programming heavy solution is basically to say, look, I have the tools now to cast this as an LP. I'm going to put it as an LP, pull up CVX pi, far away, right? And CVX pi will solve this problem for you. But can we do it analytically? Can we solve this without even having to invoke any kind of programming? So how would you go about solving a problem like this when you don't have any? So let's see if you've learned anything through the course of this class now. When you have a problem and you don't know how to start, what's the good first step to try? Write everything down. Okay, good. Write everything down. Excellent. So we've kind of written some things. What else might we want to write down? Is there anything else we want to write down? I'm not sure I have anything else I want to write down right now, but what's another thing I might want to try? Write out the piecewise functions. Okay, we could try writing out the piecewise functions. The thing that I would try in this case is I would try an example. I would play around with an example. And I would say, can I play around with this for some n points is really hard to deal with. What if I had 1? Can you solve this for 1 point? How would you solve this if n was equal to 1? If n is equal to 1, then what's the solution? X is equal to 1. Okay, so we could solve that in that case, right? What if you had 2 points? What if I had 2 points? So now I have 2 points, B1 and B2, right? What is my objective function equal to? X minus B1 plus X minus B2. Okay? So let's look at this thing. Now so where can X be? X can be over here. X can be in between here. Or X could be over here, right? These are the 3 options. This is the real number line. Okay, now think. You have to think. You have to think. I'm not going to tell you the answer. Think. Do something. Write something. Draw something. Okay, it was anything between B1 and B2. So let's think through why that might be the case. So would I choose something over here? Let's say I put X over here. Okay? Then what is this? This is basically the distance from X to B1. So it's this distance, right? Plus the distance from X to B2. Okay? So I have this plus this, right? Does that seem like a good idea if I'm trying to minimize this thing? No, right? I'm kind of double counting this part for absolutely no reason. Right? It seems like if I keep bringing X closer and closer to B1, I'm going to reduce this distance, and I'm going to reduce both of these distances are going to become smaller. So I should clearly keep bringing x closer and closer to b1, right? Let's say I put x exactly at b1. Then one of those is 0, and the other thing is b1 minus b2. Okay? What if I put x somewhere here? Okay, if I have x somewhere here, let's say I just draw this again, and this is my x. Well, then I'm looking at the gap from here to here and the gap from here to here, right? So I have this distance plus this distance. What is this plus this always equal to? b2 minus b1, right? No matter where I choose x anywhere, if x was equal to b1, this quantity is b2 minus b1. If x was equal to b2, this quantity is b2 minus b1, right? Anywhere in this range, I always have the value of this term to be b2 minus b1. So is there any difference between any of these points? These are all optimizers, right? Well, I haven't actually considered. What about beyond this side on b2? Does it make any sense to cross b2? That has the exact same problem as being on the, I guess, left of b1, right? So not in our interest. So basically, anything between b1 and b2 is a solution. What is the quantity that is like this if I have two numbers? What is this thing? What's it called? Median, right? For two numbers, we don't usually care about a median. But now let's consider this case. What if I had now many, many points? Let's say I have 7 points. Okay, let's say b1, b2, b3, b4, b5, b6. Okay, let's say I had 7 points. How could I go about dealing with this problem? Equidistant, what is equidistant? b1 and b2 are any 2 points on the real number line. They're just 2 real numbers. There's no equidistant from anything because there's nothing to be equidistant to. They're just 2 points. Pick your...
Both B1 through B7?
No, sorry, we are not. b1 through b7 are not equidistant at all. Usually I'm really bad at drawing. Maybe I was just really good this time. But how do we make them not look equidistant? Some non-equidistant points, arbitrary points, okay? Okay, so in this case now, in this more general case, what's something that you might try to look at, right? How might you go about solving this problem now? Someone else, someone else. What do you want the answer to be in this case? Do you have any desires? You kind of want it to be B4, maybe? Okay. Yeah, I also kind of want it to be B4. But how do we get there, right? So if I look at this objective function, well, one thing I could look at is kind of the derivative of this thing, right? We could look at how it's changing. Like here we made some arguments about like this is going to be big here, small here. We want the derivative to be equal to 0, but the problem with this thing is that it's not really differentiable everywhere. What are the points where it's not differentiable? b1, b2, b3, b4, b5, b6, b7, right? These are exactly the points where it's not differentiable. But it is differentiable everywhere else. So maybe we can compute the derivative of this thing, right? So basically, if I think of x minus bi absolute value, what is this thing equal to? Well, this is equal to x minus bi if x is greater than bi. And this is equal to bi minus x if x less than bi, right? So if I think about the derivative, d by dx, of x minus bi, oops, absolute value I mean, what is this thing equal to? It is equal to 1 if x is greater than bi, equal to minus 1 if x is less than bi. And what about if x is equal to bi? Does not exist, right? Okay? So now if I look at my different placements for where x could be, okay? When I think about an x that is on the left of everything, right? If an x that is smaller than b1, smaller than b2, smaller than b3, smaller than b4, smaller than b7, what is the derivative of my objective function going to look like for an x over here? It's going to be negative 7, right? Because I'm going to have basically how many terms like this are in my objective function? 7. And I get to add 1 for each of the terms, right? Or sorry, I get to add negative 1 for each of the terms. Does everyone see that? I'm doing some mental math here. I hope that's okay. Right, I have 7 such terms. And I have negative 1 for each of the terms, right? So my derivative here is negative 7. Okay? What about my derivative for x greater than b7? It's going to be 7 over here, right? What about my derivative in between b1 and b2? So now how many am I smaller than? 6. But I'm greater than 1. So what's my derivative going to be? So I have a negative 5 here, right? And by symmetry, I'm going to have a 5 derivative here. Okay? Then I'm going to have a negative 3 in between these two, negative 3 in between these two, negative 1 here, or sorry, and plus 1 here, right? This is how my derivative is going to change. Everyone with me on the derivative calculation, or did I go too fast? You're good? Give me thumbs up. Okay, good. So now, this kind of gives you a hint that, oh, well, maybe our desire is going to come true. Maybe our wish is going to come true because, hey, do we have a derivative 0 anywhere in any of these points? No. But, like, our derivative, we want derivative to be equal to 0, right? So we kind of want this answer to be somewhere in between here. So B4 seems like a good candidate. And we have everything, this prep that we've done so far. So can we use this now? So if I was to think about now my objective function, and I write this as, let me write it as B So I've just enumerated out everything, but I've just written it in a specific order, right? So we understood kind of the 2-point case. And now we want to kind of build and use that understanding here, right? So now if I consider which are the points that I'm going to want to consider, right? When I'm considering these things. If I, just intuitively, if I was to choose some x over here, is some x over here going to be my minimizer? No, right? I'm going to basically be doing a lot of double counting. X is not going to be greater than b7, right? Is it in my interest to even choose an x that's smaller than b3? I'm still going to be doing the same kind of double counting, right? So what are the x's that are going to be of most interest to me? This particular interval, right? Like I don't want to be, like basically I'm removing all of the extremes. But now if I consider any x belonging to b3, b5, okay? What is x minus b3 plus x minus b5? Always going to be equal to, when x is in this interval, b3 minus b3 to b5. Does my choice of x in this interval affect the value of this term? It absolutely does not, right? We argued that in the 2-point case over there. Right? No matter where I choose, right, if I have b3 and b5, as long as I'm in between them, x minus b3 plus b5 minus x is always going to be b5 minus b3, no matter what I do. So this term is always a constant for x in this interval. What about this term? What is this term always going to be equal to? It's always going to be b6 minus b2, right? No matter what I do. What about this term? Always constant, right? So can I ever affect the values of any of these terms by my choice of x? Nothing, right? No matter what I choose, this is always the same. So what is the term that I can affect by my choice of x? This is the only term that I have any chance of affecting. So what should I choose my x to be? b4. So what is my minimizer? b4, right? This is the median. Okay? And what we're using here is basically we're using this like kind of pairing up property, right? So b3, if you're in b3 to b5, you're automatically inside b2 to b6. And so you can always kind of generalize this 2-point case going further and further out. Now, let's say b7 was like a crazy outlier, just kept getting bigger and bigger and bigger and bigger. Okay, right? When you have data, you always have this problem of sometimes you have crazy outliers, right? And when you have a crazy outlier, suddenly your mean or your sample mean, your average can kind of get totally skewed. Have you ever heard this term that the median is kind of a robust version of the mean? If b7 was an outlier, what would your median be? It would still be b4, right? Even if you had some crazy perturbation on the edges, your median is much less, like the change in your median will be much, much smaller, or not at all, compared to the change in your mean. If b7 changed, your mean is going to change, right? This quantity changes. Depends on exact value of every single thing. That quantity does not. Okay? So by using the L1 norm, you're basically robustifying yourself in some sense to some of these changes. Okay? That's why the median is called a robust version. Okay? So write down some of these things. I'm not writing every single thing on the board. I'm doing a lot of explaining by talking. So make sure that you are taking notes in a way that you can understand this when you go back home. No, we're not breaking it into 4 minimizing problems. We're just looking at it through these 4 different terms. We're not minimizing these separately. we can't necessarily minimize each of these separately. We're just saying that some of these are invariant. Some of these terms are invariant. That's what we're saying. We're not breaking up it into 4 minimization problems.
Otherwise, had it be bound at the minimum between B2 and B, between B3 and B?
Why did we say that the minimum has to be between B3 and B5? The question is, why did we say that? Well, if I was to choose, let's say, an x here, say it's between B2 and B3, okay? Then, when I'm looking at all of my values, if I'm looking at, for example, the term, like, I have all of these things. In each of these cases, I'm doing a double counting that I need not do. Right? All of this is getting double counted. And so moving it closer to B3 will always reduce that double counting. Right? The exact same argument that we used in the 2 case argues that we want to be between B3 and B5 in this case. Right? Because that same exact double counting is going to happen here. I mean, one other way is that, well, you can, it's not a rigorous argument, but basically you want to look where your derivative is close to 0. Nothing is 0 here, but that's not a rigorous argument. That's like more of a hand-waving argument, so don't buy that argument. But the double counting argument is rigorous.
If you have an even number of points, would you take the median range?
So if I had an even number of points, the median is any point in between the 2 numbers in the middle, right? The median is not unique necessarily. The mean is always unique, but the median need not be. In an odd number of points, the median is always unique. Okay? Good. Other questions? How much time do I have? Great. Okay. So with this now, I can come to introducing the lasso problem. So far we said, well, let's look at min norm, let's look at least squares. Now, what if I was to take regularization, and instead of regularizing with the L2 norm, which is kind of what we've done for ridge regression, we choose to regularize with an L1 norm. So I want to look at the problem. This is basically what is called the lasso problem, okay? And the nice property of this, which you may have heard talked about colloquially, is that the lasso solution, or the lasso optimization problem, is good at finding sparse solutions. So what do we mean by sparse solutions, okay? A sparse solution is one where many of the entries in your unknown vector are set to 0. Okay? A sparse vector is one that has most entries set to 0. There is few non-zero entries. Okay? And in general, sparsity can matter a lot in terms of solving real problems. For example, if you're trying to reconstruct some kind of image, okay? Often it's the case that in much of your image, nothing is happening. It's a bunch of black pixels. And there's only some interesting stuff in some small number of places. Your job is to find those places. So something like that is where sparsity could be very useful. Or for example, you're doing some kind of machine learning problem, and you have many, many, many features in your data set. Okay? But only some of those features are actually active at any given time, right? But you have hundreds of millions of features. At any given time, you only care about 10. So you want to be able to solve for things where you know most of the stuff doesn't matter. And if you know that that is true, how can you use that kind of side information to get you better solutions, right? In ridge regression, for example, the side information that we had was that our unknown vector was not very large, right? And we used the ridge regularization, or as a penalty term, to say penalize large values of x, right? Don't get too large. Now what we're trying to do is we want to say, okay, penalize things where there are too many non-zero elements, okay? And that's what Lasso is very, very, very good at solving, okay? So this problem, it turns out, so to give you an intuitive idea for why this is true, it can be helpful to rethink about this problem in the following setup, is that I want to minimize subject to the constraint okay? So here what I'm doing is I have two different versions of this problem. Are these the same problem? These are not the same problem, right? But if I was to say construct a Lagrangian for this problem, it would look kind of like this, right? Right? Some terms of this. Basically what we're saying here is that here we're putting downward pressure on the L1 norm of this by saying, look, I don't want this to get too large. If the L1 norm of this gets large, I want to make it, like my objective function is large, and that's like not a good solution for me. Here I'm putting downward pressure on my L1 norm by having an explicit constraint, by explicitly saying, make sure that this L1 norm does not get any bigger than this t value, right? So turns out that you can rigorously show that you can find pairs of values t and lambda such that these are exactly equivalent, okay? So any problem of this form can be converted to a problem of this form. Any problem of this form can be converted to a problem of this form. We're probably going to give you a homework problem on how to show this rigorously, but at an intuitive level, does this make sense to everyone? That these are kind of trying to do the same things, and if you tune and if you choose the appropriate value of t, you could get the same solutions for both of these. Kind of make sense? Okay. Similarly, if I had a ridge problem, well, I would have an L2 minimizer here, right? Instead, I can think about minimize ax minus b whole squared or maybe let me call this some s. This will be a different s, right? But now when I think about these things geometrically, where should I write this? So let's look at the ridge regression problem first. I have a constraint on my 2 norm, right? I want my 2 norm to be less than t. And we drew these pictures way back in like the second lecture of this class, right? Very early on. So what does it mean for this to be less than t? If I have some x, let's say in a 2-dimensional x, that means that my x is kind of, these are the isocurves of that. As t gets larger and larger, this is what that constraint looks like, right? For different values of t, I have different values of, I have different isocurves here. Does that make sense to everyone? These are different level sets of that function, of the 2 norm of x, okay? And so what I'm saying is I want to minimize now the norm of ax minus b squared subject to a particular constraint, right? So depending on what my value of t is, I'm going to be inside one of these circles, okay? And now if I'm looking at minimizing ax minus b, well, what do the level sets of ax minus b look like? let's say I have my optimal solution somewhere here. These are all ellipses, right? And now what you're, let's say you have, depending on what your value of t is, right? If t is very small, you're going to say, well, I'm going to allow larger and larger values of ax minus b. If t is larger, then you can get smaller values of ax minus b, right? You see this trade-off here, right? As you go out, you can be closer to the solution. A solution is going to be where these things intersect. Okay? So you're looking at the level sets of ax minus b. And this is the two norm balls. Okay? So when you find a solution for this, so let's say, this is the T norm ball. The third one is the T norm ball, or the S norm ball that I've drawn there, we've written there. Then basically the only set of valid x's I can look at are the x's that are inside this ball, right? So the smallest value of ax minus b is going to be this one, right? Can I achieve this level set, which is the smaller one? I cannot, right? Because I cannot go outside this ball. So the point where these things touch is where my solution is going to be. I feel like everyone is clueless. Ask me a question or what's going on. Yes?
How do you know the orientation of that ellipse?
I don't know the orientation of that ellipse. I'm just drawing something arbitrary.
Or for some A and B, how would you be able to plot that?
I mean, how would you be able to plot that? That's basically that ellipse is being given by exactly the SVD coordinates, right? So the SVD of A will give you the major and minor axes of that ellipse. There was a homework, I think, where there was a bunch of vector calculus where you drew a bunch of level sets, where you drew in a level set like this. So go back and revise that homework. That'll help. Other questions? I think there's also a discussion problem on drawing level sets of a quadratic, also early on. Yes, the circle is centered at the origin. There's not necessarily a particularly nice answer to that. But now if I was to draw this exact same picture for the L1 case, right? What do L1 norm balls look like? Are they circles? No, what are they?
Squares.
They're diamonds, right? Or squares, I guess. So I have things like this. Okay? And again, here, I have my AX minus B level sets. My drawing is not so good. But let's draw this as an ellipse. Okay. So what is likely to happen is that similarly to this case, now if I have a norm ball, let's say I have to be inside this particular norm ball, right? I have to be inside this diamond. The level sets of ax minus b squared are very likely, not guaranteed, but are very likely to hit one of these corners. Okay? It's possible that the first point it'll touch will end up being here. But turns out that you will often hit one of these corners. And what is the nice thing about the corners of the L1 ball? They are necessarily points where some coordinates are 0. Right? This is the intuition behind why the lasso solution tends to give you vectors with lots of zeros, because you're hitting corners, because the norm ball has corners. Whereas with ridge, your norm ball doesn't really have any corners. So the ellipse does not necessarily intersect with a particular corner. Okay? So this is a geometric perspective on why lasso kind of works and why you get a sparse solution. Okay? It's not a rigorous proof. What we're going to do next is actually rigorously prove this fact. Okay? So now I want to consider basically the lasso problem. We're not going to do this in full generality, but we're going to consider this in the very simplest case. So I'm going to consider the problem min over x, say 1/2 Okay, so a scalar least squares problem with a scalar L1 regularizer. Okay? Here, x is just a real number. So how do I solve this problem? Well, remember, this is now, everyone sees that this is just finding the slope of the line ax equal to b, right? This is just finding a slope of a line, but now we have this regularizer attached to it. Okay? So let's do this in the simplest possible way. Let's find the gradient and set it to 0. Okay? Now, is this objective function fully differentiable everywhere? If I was to call this, let's say, call this thing f of x. So if I consider d by dx of f of x, well, what is this thing equal to? I have this is equal to the sum of ai squared x minus ai bi, and then I get a plus lambda if x is greater than 0, right? This is like trivial to differentiate. We've done this so many times. The kind of tricky term is this one. This is the same term, ai squared x minus ai bi. If x was less than 0, what is absolute value of x equal to? Absolute value of x is minus x. And so what is the derivative of this term? Minus lambda if x is less than 0. And what happens if x is equal to 0? This is not a differentiable, right? This derivative does not exist if x is equal to 0. Okay? So we know what the derivatives of this are. We know that this is a convex problem. So let me just set the derivative equal to 0. What happens if I set the derivative equal to 0? If I set this derivative equal to 0, case 1, right, I have x is greater than 0. Then I have right? This is what I get. Now I want to find my unknown is basically x. So this implies that I have x times ai squared is equal to minus lambda plus okay? Everyone with me here? I just did some algebra. What do I need to check now? Like I assumed, let's say x is greater than 0, and I got some value for x. But do I know that I was starting out? Like, do I know which case I was in? I don't know what x is, right? So what do I need to check to make sure that this is actually a valid solution? Like, how does this, how can I just say that let x be greater than 0 and then just choose the case that x is greater than 0? That seems awfully convenient. What do I need to check? I need to check that what I got out actually satisfies my condition that x is greater than 0, right? And so this denominator is always non-negative. That's never a problem because it's a sum of squares. But this thing, right? So this is only true if ai bi sigma is strictly greater than lambda, right? If I have that this sum of ai bi is greater than lambda, then this calculation is valid. And then I can say that, okay, this is the value of x, right? because then circularly I have still checked I'm in the correct case. Okay? Similarly, I can do the same thing. I can check if my x was less than 0. Then I can do the exact same algebra, and I would get x is equal to, I'll just look this up to avoid wasting time on doing the exact same kind of algebra. Right? But now, how do I make sure that I've satisfied my case here, if this is my value of x I get here, when I set the gradient in the second case to be equal to 0? I need to make sure that this term here is negative, right? So I need to basically say that it is only true sigma ai bi is smaller than negative lambda. Right? Does everyone see this? And in all other cases, so if sigma ai bi is between minus lambda and plus lambda, if I'm in between those two values, what must then my x be? Right? If I'm on one side of lambda, right? So let's consider the real line. This is 0. This is plus lambda. This is minus lambda. Okay? If sigma ai bi is greater than minus lambda, then my x solution looks like this, right? This is sigma ai bi greater than lambda. If I have sigma ai bi less than minus lambda, I have a solution that looks like this. And now if I have sigma ai bi in between minus lambda and plus lambda, what do I have as my solution? X is equal to 0 is the only choice left, right? Because x cannot be greater than 0. X cannot be less than 0. So what must x be? X must be 0, right? And so this is what your solution for x will look like. Okay? What happens when the case lambda is exactly equal to 0? When lambda is exactly equal to 0, that's just your regular least squares problem, right? There's no regularization. In that case, your solution looks exactly like this, which is exactly the least squares solution, right? Sigma ai bi divided by ai squared is exactly the scalar least squares solutions, A transpose B divided by norm A squared, right? When this is 0. So this is exactly what you expect to have happen. But now you're seeing that basically by choosing lambda, you're choosing a range. The bigger lambda is, the more likely you are to set x to 0. Right? Do you see here that as lambda becomes larger, this middle interval where x is becoming 0 is becoming larger and larger? Okay? So through this example, like we haven't proven this for the vector case, but for this scalar case, do you see why the L1 regularizer forces sparsity? It forces x's to be 0 as compared to least squares, or even as compared to ridge. Right? Everyone see this? I will show you an example in class next week with a Jupyter notebook that shows this. It's going to be on your homework. It's super cool. Okay, that's it. See you next week.